Okay then, today we'll be covering projectile motion. So before we get started, I'd like your guys' inputs on what do you think projectile motion is. So just so we can have a more interactive session.
I'm sorry, what was that? I bugged out.
Okay, cut that part out as well. So guys, today we'll be covering projectile motion. Before we get started, I'd like your guys' inputs on what projectile motion is.
So I think if something goes like kind of in a parabola shape, it's a projectile.
Um, I think it's in like at least in my perspective, this definition would be something that of an object undergoing the force of gravity in a motion that can be uh, put on a graph, and it would take the shape of a parabola, similar to Kuchaga's opinion on it, I guess.
Okay, those are all really close to what projectile motion is. And in this presentation, or whatever you can call this, we'll be covering how we can calculate the time taken for the object, the distance, and the maximum height. And the only thing which is required is the initial velocity and the angle which you throw it out. Well, let's get started. Now I'll be answering the question which I posed earlier. What is projectile? Well, projectile motion is the motion of an object when thrown into the air. Now, a fact about projectile motion is that it's only subject to gravity and nothing else. So this means that other than the initial force which you apply, there's nothing else acting on it, and gravity. We're going to move on to the time taken. Now, I'd like you guys to watch this video I have prepared.
Okay, hello guys. Today we'll be talking about projectile motion. And well, let's just get started. So the main things, right now I'll just get out of the way what we're going to be using to represent everything. So this will be the y-axis, this will be the x-axis, and this will be the path the projectile will take. This will be the initial angle which the object is thrown at, and this will be the initial velocity. Now what I can do here is I can draw a triangle, this right angle triangle here. To better enunciate this, I'll redraw this triangle over here. So now I can write this u here. I can write this as u, and this is the angle which the object is thrown at. Now using these two, I can write this as u sine theta, and I can write this as u cos theta.
Okay, so before we go any further, I'd like to get a few things out of the way first. U in this case is initial velocity, and anything else where I'm not going to be showing all of the working. Anywhere else which I'm not going to be able to show all of the working, you guys can try it out for yourselves and convince yourself that it actually works, because it's kind of like a small exercise for you guys.
Okay, just now we found out what the time taken would be. I've already stored this, and we'll save it for later. Now, if we go back to our initial diagram here, or however crude it looks, now for sake of visibility, I'll redraw it here. For now, all we're going to require is this head and this range and this g, the acceleration. Now, as you can notice, in this projectile's path, this is the point where there is no more, like this is the highest point, which means there's no vertical acceleration at all. So the vertical component is it's at its highest point. And also, because of this, as we've determined earlier, that means there's also no horizontal acceleration, because we are the only acceleration we get is is the gravitational one. So therefore, I can write the distance r equals the horizontal component u cos theta multiplied with time, because speed equals distance upon time and distance equals speed times time. Speed equals distance upon time, sorry. Yeah. Now, as we've just discovered, t equals this right here. Now what t equals this, and we can just get rid of this. And now if we multiply these two, we have r equals u square cosine.
One moment here. I'm just gonna pause the video
Theta.
for a second. It was at this point I just realized I made a small mathematical error without realizing. This is actually supposed to be 2u squared, and I didn't realize that at the time. So just ignore that bit of
Times sine theta by g. Now cosine theta and sine theta can be just presented as.
One more thing, in the end, I fix up the error by just magically reinserting a 2 in there. But in the end, it gets the right answer. There's supposed to be a 2 in there.
Right.
U squared sine 2 theta by g. Now we have an equation for range. Now I'm gonna save this like I just did with time earlier.
Next, we'll be concerned with maximum height. Now we just covered the horizontal range, and now we're just gonna apply the same thing but vertically, and make a few observations along the way.
As we just covered, r equals u square sine 2 theta by g. R represents the horizontal component, and now we're interested in finding the vertical one. As you can hear, my voice is really dull, so this is like the 6th or 7th attempt at doing this. So that's just my problem. So I'm going to be representing this point of maximum, or this maximum point. Well, it's at this point where the vertical velocity is 0. So I'm going to be representing that with vy equals 0. And using the equation b squared equals u squared plus 2as, we can find out the value for h. Now what we can do is substitute all the values. 0 equals u sine theta whole square minus 2g h. Solving for h, we get h equals u square sine square theta by 2g. You can verify this for yourself, because in this case, square and v square, I'll be substituting vy and uy. And uy contains the same logic as applied for vy. It's just the vertical component of the initial velocity. And you can verify for yourself that this works.
Yeah, so that's it. That's projectile motion for you guys. Now, projectile motion contains like lots of things, and this is just like the bare bones of projectile motion. There are many other things. Like for example, there is a way to prove that the range when you have like two angles such that theta equals say 25 degrees and theta 1 equals 90 minus 25 degrees. When the two thetas are complementary, the ranges are the same. You can mathematically prove that as well. And I've actually recorded that, but I've lost the video. So that's it. That's it for today. Thank you for listening about projectile motion. These are like these three formulae are the main things used in all of projectile motion, and that's the whole concept. Like most of projectile motion is just dividing the components into the vertical component and the horizontal component, and these three are the main things which tend to be asked whenever it's like required. Right. I guess that's it. If you guys have any feedback or anything like that, I'd like to hear it now because I'm not good at this.
I had a small idea about our previous discussion on kinetic energy. Can we try proving the maximum height formula by equating the kinetic energy and the potential energy?
Right. But the potential, you mean gravitational potential?
Yeah.
So the kinetic energy in this case. Wait, could you please repeat? I didn't quite get what you said.
See, so basically the maximum height is dependent on only the vertical component, right?
Yes.
Like you mentioned earlier.
Yeah.
So if we find the kinetic energy that includes only the vertical component, like kinetic energy of the vertical component, then and can we equate it to the uh, gravitational potential energy, like mgh, and we can kind of find another formula for height, maximum height.
And then equate them together and just go from there, you say.
Yeah, can you try that on a whiteboard once? I just want to see if how conservation of energy works with vectors.
Yeah, we can try that, but the problem is I don't have a whiteboard on me, right? So you see those videos I recorded on the iPad. Right. So do we have any other questions? I'm gonna assume that-
I don't have a doubt. I'm just like wondering, uh, like how exactly is like projectile motion related to solely just gravity? Because like there's many other forces that since your definition included only to the it mentioned only to the force of gravity is where it's measured. So there's a lot
Right.
of other.
Yeah, right. I've been waiting for someone to ask that actually. So the thing is, uh, there are other forces, but the thing is, they're just not that necessary. You don't really have to take into account. If you have the initial velocity and the gravitational constant and the angle, those three are actually just enough to calculate everything you need. And you can get the initial velocity by doing f equals ma or some other formula like that. But like you can like use that. But the aside from the initial force which you apply when throwing the ball, the sure that like the initial velocity which you get from that is the only thing which is required. So that's why it's not really included in the definition.
Mamsi, I think
It's
we
just
can assume that the force with which the projectile is launched initially is just cancelled off by the air resistance, and there's no net horizontal force.
But if there's no net horizontal force, then that means it's not accelerating.